that in mind, I'm telling you to solve these differential equations by separation of variables, right? Which means that they must be a proportional relationship. If they're not, then you'd have to use a different technique. And so since I told you what technique to use, you would assume that one has to follow the other. All right, so cross multiply, dy equals 2x dx. But again, that dy is really a 1 dy. Integrate both sides. We're looking at y equals x squared plus c. Sometimes they're just really nice. All right. But, you know, it's kind of like taking something that you would think of as an easy problem, and it's just like, oh, we're making it unnecessarily more challenging. But we're really not. You know, because really it's just this additional step of redefining it as a differential equation in differential form before integrating. All right? But if you remember, this was the very first example in the entire packet. Like, whatever number of pages ago. 1 million pages ago, 29 pages ago, 28 pages ago. So, long time ago. Right? This is where we started, but it still falls into this concept of separation of variables. Right? Number 8, same idea, get it into differential form. It's kind of rooted in the familiar somewhat. Right? We're looking at dy equals 1 over x dx. But again, it's a 1 dy, so you integrate. We're looking at y equals antiderivative of 1 over x, ln of x, plus c. We don't have to do anything fancy here with the exponentials, logs, things like that. It's because there is no exponential or log, so we're building towards that. Number 9. The y's are already on the left, so I'll just move the x's to the right. 3y squared dy equals really a 1 dx. Integrate. What am I looking at here? Y cubed. And what about on the right? And we'll have an x. All right, I purposely left a little gap there. Yeah, I'm thinking put the plus c on the left-hand side. The reason I'm thinking that is because generally what we had been doing is solving for one variable in terms of the other, but explicitly. So y in terms of x. This one kind of naturally worked out to be x in terms of y. So if that's the case, you're not really accomplishing much by saying y cubed equals x plus c. You haven't solved for anything. You haven't solved for y and you haven't solved for x. Right? So unless you want to introduce a cube root, which is well within your rights, if you did that, you'd be looking at y equals the cube root of x plus c, which is a perfectly acceptable final answer, but apparently not at the time that I made the answer key, because I guarantee you on my answer key it says that, but this is the better answer. Sometimes you shift your focus and think of things explicitly in terms of x rather than in terms of y, all right? But maybe your instincts don't take you in that direction, in which case you would say, it's all right. Or you might have said y cubed equals x plus c, and then take the cube root of both sides. All right, so it's a good answer. It was good enough for me. I guarantee you this is what I have on my answer. But this is the better answer, obviously. I think once you really kind of consider what it is you're after, then it becomes obvious why this one's nicer than this one. And again, the idea is explicit form, solve for one variable in terms of the other where possible. All right, so I'll get to that in a second. If it is possible, it might look better in one form as opposed to the other. So choose the form that makes it look nicer. Why do I show both ways? You know why. And in case you don't, multiple choice. All right. dy dx equals x squared y. Proportional relationship, product of x squared and y. So 1 over y dy equals x squared dx. Integrate, integrate. Natural log y equals 1/3 x cubed plus c. All right. We want to solve for the variable that it makes most sense to solve for. In most cases, that's y. But since x is raised to the third power here, odds are that's probably not going to be the nicer variable to solve for. All right, so exponential form, we're looking at absolute y equals e to the 1/3 x cubed plus c, which transforms itself into what? C e to the 1/3 x cubed. All right. Once, like I said yesterday, once the c becomes a coefficient, that's your license to drop the absolute. All right. So if in your next step you show the intermediate move of e to the 1/3 x cubed times e to the c, but still not enough to get rid of the absolute. All right. E to the c doesn't absorb anything. C absorbs everything. All right. Everything that's constant anyway. Number 11. So this one's pretty clean. Y plus 1 dy equals 2x dx. Integrate, integrate. You don't really need the parentheses. We're really just taking the antiderivative of y plus 1, which would be what? Y squared over 2 plus y, very good. And then on the right-hand side, we'd have the x squared plus c. This is an interesting case because depending on what your objective is in the problem, this may be nowhere near good enough. Right? First thing I notice is that we have a power of 2 associated with both x and y, which means it's a conic. All right, if it's a conic, that means there's a standard form for it. All right, which is really not quite what you're hoping for, because you want to be able to solve for y in terms of x, or x in terms of y, but you have to, in these cases, be prepared to put it in the appropriate standard form for that conic. All right, first thing I'm going to do is multiply everything by 2, get rid of that fraction. So y squared plus 2y equals 2x squared plus c. All right, I'm going to bring the 2x over. No, 2x squared, sorry. I'll leave a little gap here. What should I pop into that gap?
Zero.
That's 0. I guess the first thing is figuring out what technique I'm looking for here. Completing the square. So completing the square, what do we do? What's the process? Have that b value is half and squared. 1. So add 1 to both sides. The reason for that would be so that we create a perfect square trinomial, y plus 1 squared, and then we have the minus 2x squared. Sometimes you do have to complete the square for both the x and the y stuff. That could be more entertaining, but in this case we didn't have to. So what we get from this is the idea that we're looking at a hyperbola, and also we know the center of that hyperbola would be 0, -1. Now you can get dimensions based off of that, but sometimes that's all you need is just to get a sense of the graph. That being said, if all you need is the sense of the graph, let's say you're looking at a multiple choice question in which you have your various choices, and you look at the different possibilities, and you say, okay, well, that one is the equation of a parabola, that one is a trig function, that solution is a log function, and then we have this hyperbolic function. If you recognize it as hyperbolic, then maybe you don't have to do any of this differential equation stuff, separating variables. Maybe you take a quick look at the slope field and see if that kind of points you in a direction. Right? So my window, let me just make sure it's good. Well, probably a little bigger.
Hyperbola wasn't a function.
What's that?
A hyperbola was not a function.
It's a function, but not in rectangular coordinates. It's a polar function.
Right.
So that's the thing. When you learn enough stuff, words like functions become interchangeable with equations, unfortunately. Sometimes I have to remember what level I'm teaching, because I call everything a function in Algebra 1, and it's just not true in that context. But then you get to higher level calculus, and just about everything is a function. All right, so 2x over y plus 1 would be my differential equation. Then I'm going to run my program, slope f, because it didn't have enough characters to write the entire term, slope field. Run it. That's like screaming hyperbola. I mean, assuming you know what a hyperbola looks like, that's the thing. If you don't, then it's not, well, it's still screaming, it's just not screaming that. Right? So that would be the issue. But yeah, just imagine a case, test, quiz, AP exam, multiple choice question that says which of the following is the solution to the differential equation. If it's multiple choice and you're allowed a calculator, maybe you don't have to do any of this. Maybe you look at the slope field and see which equation in your choices the slope field seems to correspond to. All right, that's one of the reasons why I give the program, because when I talked about creating slope fields yesterday, I described it as a tedious process. It doesn't seem to have much value, the idea of constructing it. But the idea, especially in terms of test taking, the idea of actually using a slope field to your advantage, very, very, very important.
What was the exact number you put in your calculator for the function again? I'm sorry, I didn't. Okay. Thank you.
No problem. All right, so, but again, only multiple choice. If it's calling for a particular equation, then you got to do it, So, this last one, we have to add the 4x to both sides, 1 plus y dy, well, dy over dx. Let me just not skip steps here. Equals 4x, then multiply. This one seemed at first glance, because it had more stuff, that it might be a little trickier. It's actually not too bad, because everything is reverse power rule. All right, we just had to slide some things over. Off the bat, it didn't look like it would necessarily be a proportional relationship. It's kind of weird to think of it this way, but if you have a function that's in the form, so a differential equation also can be modeled after functions. If you have a function that's in the form of y equals mx plus b, that's a proportional relationship. Well, specifically 0 equals mx plus b, the m being your derivative. So a particular function, one of them multiplied by a slope, that's following a linear relationship. And so later on in the course, when we learn about linear differential equations, we're basically learning about something along these lines where it follows the concept of a linear function. It's pretty cool stuff. All right, so integrate y plus 1/2 y squared equals 2x squared plus c. All right, so it's not too bad because we have the recipe. We know what we're supposed to do. All right. Actually, it's kind of more than a recipe. It's like a blueprint. It's almost a step by step. The only difference here is that we have a 4x really instead of a 2x. So we're going to look at something that's double on one side what it was previously. But we could still follow the same idea. It's a conic because these two exponents are 2's. Double everything. So 2y plus y squared equals 4x squared plus c. All right. No need to reinvent the wheel. Add 1 to complete the square, which gets us y minus 1, I'm sorry, y plus 1, this is right in front of my face, squared minus 4x squared equals c. All right, so it's basically the same. You could have jumped right to the same answer.
What happens to the plus one on the right side?
Oh, c absorbing.
Oh.
Yeah, it's
okay.
still an absorbing constant.